Okay, let's get started. So today, let me back up already. On Monday, we learned everything that we really need to know about linked lists in order to do task 1 of the homework. And then Wednesday, we reinforced that. We got into a memory diagram so you can get some help with the quiz. And today I want to get more practical and get into IntelliJ. I'll spend this whole lecture in IntelliJ and show you more practical things of how to apply this concept to your code. And I want to focus on 2 things, the debugger and testing. I've shown the debugger a good number of times so far this semester, so I want to get in there again, make sure I get another example, because I'm still having students in office hours where they'll come to me with their code, they'll say, my code doesn't work, Autolab doesn't like my code, and I'll say, what did you learn when you ran the debugger? And they'll say, what's a debugger? I hope that that's a small portion of the class, but I still want to give more debugger demos, just so I can show more debugger stuff. But there are some of you still not using the debugger. It's possible that they're the empty seats also. I wouldn't be surprised if they're the ones that don't show up to lecture either. But there's a good number of students who just aren't using the debugger. I don't want to harp on this too much, but I want to at least kind of remind everyone what my thoughts are on this, I guess, and give some advice. I believe that if you write really good test cases, and then when those test cases fail, when you expose a bug, your test cases, the whole purpose of a test case is to expose your bugs. Once your test case fails, if you run the debugger to find out what's going on with that, watching the state of memory. If you do that, you'll solve probably 98% of your problems on your own in almost no time at all. You won't need office hours, you won't need Piazza, you won't need me and the TAs to help you out. You'll just be able to solve all of a lot of your issues. Now, granted, sometimes there will be cases where, my test case just isn't playing nice with your code. There's just some specific thing that you didn't test for. And I get that, and when I see those questions in office hours, I usually give you pretty heavy-handed hints as to what's going on, what my test case is doing. Most office hour visits, Piazza posts, are not like that. They're usually questions that you could just answer yourself if you ran the debugger. So I want to do another debugger test. And I don't want to say it's a large portion of the class, so I don't like doing these things and talking to the whole class, because most of you probably don't need to hear it. Most of you just write good tests, run the debugger, and then I never have to see you because you just get your shit done. So I don't want to spend too much time talking about it as a whole class. So with that, let's do another debugger example. I'm going to go through this, not the entire thing, but the memory diagram example that we did last time. I just want to show you how the same thing looks in the debugger. So I'm going to set a breakpoint, and when you're trying to debug something, you want to set the breakpoint at a meaningful location, where you think the bug is occurring. So you don't want to run the debugger and test things that you know are correct. So in this hypothetical situation, let's assume that we know we're creating a linked list properly. We know that we get this list 531, and all that's working fine. And then I want to debug the value. The value is giving us the right value, but I'm going to set a breakpoint here so I don't have to click through all of this code. I'm just going to get right to some code where my potential bug would be. I'm going to set my breakpoint there and then run this in the debugger. And it's going to stop at that breakpoint and show me all of the state of stack and heap memory, everything that's going on in memory here. So when I run that, I should be able to see my list. It's the only variable that I created on this stack frame. I'll be able to see my list. As always, we also have args in this for the main method. Again, we're not concerned about either of those in CSE 116. But my list, if we expand this, we see that it's a reference to a linked list node at 801. We don't care what those numbers are. We just care that number means reference to something on the heap. So we see this 801. It has a value of 5, and we will often see strange things in the debugger that aren't quite what we expect. Some of this is compiler optimizations. Some of this is I'll just stick with compiler optimizations, where right here we have an integer that looks like it's at a reference on the heap. In our memory diagrams, those are going to go on the stack, but oh, actually, I know why that is. It's because it is on the heap. It's part of my list. So it is technically on the heap. But we have the value 5, and then next, referring to a linked list node at 803, which has the value 3, and a reference to a linked list node 805. We got really consecutive values here, 801, 2, 3, 4, and 5, and 6. And then value of 1 and next of null. So we can see our entire linked list on the heap, and we can follow these references to see all these nodes and how they link together to form this one list. And then when we're running our line of code that we're looking at, the value is mylist.next.next.value. Mylist.next.next.value is going to be 1. Now on Wednesday, and a few times earlier in the semester, but most recently on Wednesday, for this exact line, I said that when you're looking at the code, if you don't have any way to visualize memory, if you're just looking at this code and trying to decide what mylist.next.next.value is, it can be kind of tricky to see that. It's a common mistake is to think that this is the list 1, 3, 5, and think that the value is going to be 5. It's easy to make that mistake. But I had the memory diagram up at that point, and I said, I keep stepping on this thing. And I had the memory diagram up at that point, and I said, we're not going to look at the code, we're just going to look at our memory diagram. We're going to go my list, follow the reference of next, follow the reference of next, and then grab the value right there. And it was trivial when you had the memory diagram. There's one big problem with that, is after 116, you might never write a memory diagram ever again in your life. It's one of them things where memory diagrams we use as an educational tool to sit down, here's some code, draw the memory diagram to show me that you understand what happens when this code runs. Once you've proven that, by the time you get done with 116, you will have proven that. I think you'll see memory diagrams in 220, by the way. I don't think they require you to write your own memory diagrams yet. I think they use them just to show you things. It's possible, though, that they have exams with memory diagrams where you have to write them. I'm not 100%. But at the very least, after 220, nobody's going to ask you to write a memory diagram. No, you're never going to write a memory diagram for your career. You're never going to do them again. Once you've proven that you understand how code executes and how stack and heap memory works, we don't need you to do that again. But it's still helpful to see that information, and that's where the debugger comes in. The debugger is going to be your long-term takeaway from memory diagrams, is that you can run the debugger and visualize the stack and the heap by following references here to see all of this information and do the same thing that I said, with the memory diagram, you can just look at it easily. Well, with the debugger, you can do the same thing. Mylist.next.next.value is 1. 100%, like I know what's going on with that because I can see it right in front of my face. I can see the state of memory. I don't have to read this code and figure out exactly what's going to happen and look at my linked list node and say, okay, am I prepending? Am I appending? Like what's going on here? I'm just going to look at my debugger. So the debugger is your long-term solution for memory diagrams. Using the debugger, knowing how it relates to what you've done in memory diagrams is a very critical skill moving forward in your career. Let's advance this debugger a little bit. We're going to print out 1 to the screen. And the next thing, we get to size. We're going to make a call to size, put a frame on the stack, where this is the head of that linked list that we just saw in the main stack frame. This is a reference 801 to the same exact linked list node that we had a reference to in my list on the main stack frame. It's the same exact thing, 801, 801. Then we're going to call sales tail rec for tail recursive of 0. We're going to put another frame on the stack. which is going to make a recursive call. Again, we have the head of the list, which refers to the rest of the list in size of 0. And at this point, so on your memory diagrams, you're going to put a few more frames on the stack, and then it'll return the recursion and everything. But I want to show something a little bit new. We have this set up as tail recursion. I mentioned this on Wednesday. Again, I just want to make sure this is very clear. You don't need to know about tail recursion. This is more of a nice to know kind of thing. You don't need to know about tail recursion for this course. If we do end up giving you a method that has tail recursion on it on the quiz, you should still draw all your stack frames just like we did in the memory diagram on Wednesday. But when you run the debugger, you're going to see what actually happens when we have tail recursion. Where again, tail recursion is where the recursive call is the last thing a stack frame does. Is when we make this recursive call, this tail recursive call, we're not going to get another frame on the stack. We're going to reuse that location for the previous stack frame. Isn't that amazing? I'm amazed by it. We're going to reuse the memory location of the previous stack frame because that stack frame is done. It doesn't need to do anything. Whatever this stack frame returns, it was going to return to that other stack frame, and that stack frame was just going to return it without doing any extra computation. So let's just get rid of the middleman, get rid of that other stack frame, and just replace it with this new stack frame. We're going to make another recursive call. We'll see the same thing. We're not adding more frames to the stack because this is tail recursive. And then when we get to the base case, we're going to return right to size because we didn't add all those stack frames to the stack. They didn't exist because the compiler is able to optimize this for us to be able to not add more frames. This is very handy. This is much preferred over regular recursion when you're writing actual code. Again, in 1.16, you don't have to care about this. But I want to mention it because it came up. But this is much preferred to regular recursion because, one, it saves memory. Like you don't have to allocate, you don't have to use up stack space and then remove that, free up that stack space. You don't have to do that. That's, in my opinion, kind of a minor advantage to this. It does save a lot of memory. But the bigger one, the more, in my opinion, more important one, is that you're avoiding stack overflows. If this recursion goes down 10,000 levels, you don't have 10,000 frames on the stack, which is probably going to hit a stack overflow error. You're not going to hit that stack overflow with tail recursion because you only put one frame on the stack. How are you going to overflow the stack when you're only adding one frame to it? It's not going to happen. So then you can have recursion that has millions, billions. You can have trillions of recursive calls. If they're tail recursive, you're not going to overflow the stack. It opens up the potential for recursion to work on really large problems without having to worry about space issues with the stack. And this returns and we print to the screen. Again, if you go over to console, you can see what was printed to the screen. The value 1, size 3. Any debugger questions or anything specific you want to see? Because at this point, I'm just assuming you know how to use the debugger. And I'm just showing you like new examples, the new content with the debugger. So if that assumption is false, let me know and I can show you debugger stuff. Yeah. So, debugger a lot. Good. Yes, I love hearing it. Yes.
And then, as far as I understand the IntelliJ debugger,
Correct.
following the
Yes. I want to try to set up an example for you, and then I'll repeat the question for everyone. Let's say my list equals list my list dot size. So let's use Scala's list length. Actually, let's get a little spicy with it and prepend. Wait, why? It wants me to import that class. I'm not reassigning it, so it shouldn't be the val. But why is it asking me to import? What am I doing wrong with this basic code? Maybe it's because I'm running the debugger right now. What was the? That's what it is. Thank you. Okay. So the question is, I'm running the debugger. I'm having a great time because the debugger is amazing. And then, I'm paraphrasing, of course. And then I find myself deep into Scala code. And I get lost, and everything sucks at that point. So I'm going to run the debugger. This should get me into Scala code. When I prepend to, once we get there, so the TLDR is going to be this button right here, the step out. But I'm going to step into, of course it didn't go into it. Why didn't it go into the prepend? Oh, brother. Because I'm not going into main? It was being run though. Wait, let me just set up something else because I don't want you to just watch me struggle. Plant L's should work, right? Kind of wanted to show some list code, but it should run this code. It was running it, it just wasn't going into the Scala stuff. Usually I have problems with this happening on accident. Now I can't even get it to do it on purpose. I'm just going to set a breakpoint inside Scala just to get the behavior we want. Okay. And we step into, and then here we go. We're deep into Scala. We got all kinds of stuff running the split method, and we're deep into Scala and we're lost at this point. We can see on our stack frame that we have two internal calls, and then our stack frame, which is waiting right here. So when you do get into Scala, you're going to hit this button right here, the step out, and that's going to exit the current stack frame. So it's going to run until this stack frame ends. So when we get to the end of this method and return, that's when we're going to get control of our debugger again. So we just completely got rid of that whole stack frame. And then we're still in Scala code here. So I'm going to hit it one more time. And in general, I'm just going to hit that until I get back to my code. When I get back to code that I'm concerned about, and then I'll keep going. But there is no back up button. You can't go back one step. So whenever, like even during lecture, when you see me go past the point that I wanted to talk about, I'll have to rerun the entire debugger. I'll sometimes set a different breakpoint and then rerun the whole debugger because you can't go backwards a step. But when you get into Scala, just hit this step out. If I hit it one more time, it'll run the rest of my program. It should have. And then I'll be at the end of everything. But step out is the big one that you're looking for. Okay, and the other side of the coin of debugging is, of course, testing. Now, testing I force you to do, so I don't have to preach as much about it, but I am going to get a little preachy today. Sorry in advance. But I'm going to write some test cases. I want to spoil some test cases. It's a Friday after all. Every Friday I try to get test cases. I've been pretty consistent this semester. I did miss one Friday, I think 2 Fridays ago, I believe. But I'm going to clone this repo and show some test cases for task 1. So I already accepted the assignment. I already have my repo created. I'm going to clone this code, go into IntelliJ, and I haven't set up a project from scratch like this in a while, so it's time to do that right now. I'm going to go to git, clone, paste that URL. Since I just created this repo in the previous lecture, I already have a directory named exactly this. So if I click clone, I'm going to get an error here. Directory is not empty. I'm just going to hit it with a -2. Just something so that directory name is something different. If you've ever cloned a homework project twice, you've gotten that error. You've probably gotten that error unless you were really heads up and saw it coming. But I'm going to clone this repo. I'm going to go to my source directory. I'm going to right-click it, mark directory as sources root. So we're going to have multiple directories. Like I have this idea directory with all the IntelliJ configuration. And I have this source directory. I'm going to have a target directory, an output directory, I believe it's called. Target, it doesn't matter. You're going to have some directories here. You got to tell Scala you got to tell IntelliJ which directory contains your code. Which directory should get analyzed for syntax errors, which directory contains all the stuff that IntelliJ should be worried about. If you don't do that, then your project technically doesn't contain any code in IntelliJ's eyes. So we're going to say this is the directory with the code, not this directory. I don't want you to analyze this for Scala syntax errors. This directory is the one where all the code is. This is where all the good stuff is. And when you first clone this repository, there's a lot of stuff. Now for earlier homeworks, especially in this course, I don't like giving large projects as handout code where there's just an overwhelming amount of code right from the bat. By the end of the semester now, I'm more comfortable doing that. After all, this is a course about building large programs. To ask you to write an entire large program is a little bit overwhelming. Some of you argue that what I asked you to do now is overwhelming, so having you write this whole thing, I'll have a mutiny on my hands. So to have you get your hands on big projects, I got to give you a lot of code. It's just kind of the nature of the beast. But to manage the complexity of that, all of the methods that you have to write are in this AI player class. So go to game, enemy, AI player, and here's where all of the methods for all of the tasks go. So at least localize where you write your code. You can, of course, add more methods, more classes, more packages. You can add your own stuff, but this is where all the required methods are. And then it's only minimal extra stuff that you have to understand. If most of this stuff you don't want to look through and you don't want to understand it, it's 100% okay. But your code that you write will live in a larger project. And I want to give an example of that. And then those of you interested in the larger project, by all means, please read through all that code, ask me questions in office hours how it works. I'd be happy to talk about it. To run this code, you'll go to game server. Now this is set up. Oh, I forgot to set things up. And then you'll usually get this set up Scala SDK. You just click OK, make sure the version is right, 2.13.8. And then you're all set up with the project. This is set up as a web app, so I'm going to run game server, and I'm going to see this warning, and then some red text come up. That red text is not errors. This always trips up at least a few students. This is not an error. For some reason, and I don't like that it does this library likes to print things out in red. Whenever I see red text as a developer, I get scared because it looks like an error. This one is not an error. It says right here, this is info. And then once it's running, go up to front-end index.html and either click one of these buttons here. Sometimes these buttons don't work. You need to go to File Explorer or Finder or whatever it's called in your operating system and double-click the file to open it. I'm going to open this in Chrome, and I should see the game. If the server's running, the game should pop up. I can move around with the arrows. I can fire with the spacebar. I have effectively a machine gun here, and I can hunt down these AI players. The AI players are just moving around randomly. They're really dumb. Makes the game kind of boring. There's no challenge to it. You're just walking around shooting the AI characters. Your goal of the homework assignment is to make them smarter to the point where they're going to hunt you down and shoot at you as well. They do have the power to shoot, they just never hit their space bars in the starter code. So, get this set up and spoil some test cases. So test cases are important. Testing your code in general is critically important. And I feel like this point sometimes gets lost in 116 because I do force you to write tests. Don't get stuck in the habit, which some of you have. It's hard to gauge like how widespread this issue is, but a lot of you get stuck in the pattern of if Autolab says my tests are good, then my tests are good. That is not true. That is absolutely not true. That just means you got rid of my incorrect solutions, which are usually like pretty incorrect. Like they're pretty. Most of them are pretty bad. Some of them, don't get me wrong, some of them are tricky and do take you hours to find tests for to get rid of them. I don't want to belittle that. That is challenging. But a lot of them are pretty bad. And specifically with task 3 of project 2. This is the first time where I really backed off, I guess. A lot of my incorrect solutions are fairly overbearing. I'll have like 8 or 12. I'll have quite a bit of incorrect solutions that are making sure that you're testing a lot of different things with your code. By the time we got to task 3 of project 2, I'm backing off and saying, look by this time, I've forced you to test. You understand how testing works. I'm going to let you test your own code. I'm just going to have, I think, 3 incorrect solutions, which are like really incorrect. It's easy to write like potentially 1 test case and have Autolab say, yeah, your tests are all right. And then what I end up getting in office hours is a lot of students failing my tests 3 and 4. And then I say, well, show me your tests. And their tests are just a pile of garbage because Autolab said their tests were good, so they stopped writing tests. And this has been scaring me over the last few weeks, or worrying me, concerning me, because if that does describe you, you're missing the idea of test cases. I don't force you to write test cases because I want you to, well, I do want you to understand how testing works, but I want you to write test cases to save you time. If you write test cases and test all the functionality, like for task 3 of project 2, if you just sit down and write test cases for every piece of functionality that's defined in the document, and then run those test cases until they pass, edit your code until those test cases pass, you won't need Autolab, you won't need office hours, you won't need Piazza, you won't need any help. You'll be able to write that code just fine on your own. Of course, you might have trouble implementing the state pattern. You can ask us questions about that. But you won't have these mystery questions like, what the hell is your test, the checkout process? What does that do? Which, by the way, is my giant test, which just does a whole bunch of stuff. It just basically whacks all the buttons for a while and then makes sure everything works well. If you have tests that's doing the same thing, you won't have to worry about what my test does. You'll just have your own test that does the same thing, and it'll be fine. But a lot of you wrote almost no tests, and then were wondering why your code was failing my tests, which is concerning. I didn't mean to go on this long of a tirade on this, but which is concerning for a specific reason. So let me wrap this up. Which is concerning for a specific reason. After 116, nobody's going to test your tests. Autolab, in any other course that I'm aware of, I don't believe anybody else is testing your testing like I do in 116, because presumably after 116, I taught you testing, you know how testing works, and then you go off in other courses and you just do your own testing without being forced to. If you're not internalizing that idea, 220 and 250 will be hell for you. You need to be testing your own code, internalizing this idea of testing, and just writing your own tests to be able to make sure that your code works, even when you're not forced to, or else you're going to be pulling multiple all-nighters per week. You're going to be spending hours and hours on homework assignments that you don't need to be spending. But if you just write your own test cases, thorough test cases, and then when those test cases fail, run the debugger, you shouldn't have too much trouble with computer science or programming as a profession. You shouldn't have too much trouble. It will save you tons of time and frustration if you internalize these ideas, write your tests, and run the debugger. If not, you'll be one of those students who fails out of 220, 250 and says, this is a weed out course. Computer science is trying to get everybody to fail 220 and 250. I hate hearing those things, by the way. We're not trying to do that at all. But those courses have a reputation of being weed out courses. And I think in part because we kind of back off on forcing you to do certain things like testing, running the debugger, not submitting to AutoLab 1,000 times, things like that. So I just want to give you a heads up, really, is internalize testing now, and it'll save you tons of frustration in the future. But I know some of you won't listen to that and then still say, oh, this is a weed out course. They're trying to get us to fail, but it is what it is. I've said my piece. So let's do some testing. So testing for task 1, we want to create some linked lists. So first of all, these are methods. For task 1, locate player, closest player, and compute path are the 3 methods we want to write and test. So locate player is going to take a player ID and a linked list of player locations. And this is a method of a class. So to call a method of a class, just like in Learning Objective 2, in Project 2, we need to create an object of that type. So I want to create a new AI player. And I can see that the constructor is going to take a string, which is the ID of that player, and I'm just going to name it player1. I need to import AI player. Since this is in a different package than AI player, the task 1 testing is in a different package, I need to import that. So import game.enemyai.ai player. And then when I call this, I'm going to eventually call this player.locatePlayer. I'm going to give it some ID, let's say AI3, and some list of player locations. I'm going to make sure, and then I'm going to assert that this is, I do that every time, and make sure that that is what I expect it to be. I'll have my asserts after that. So that's the setup that we want. And now we got to create this linked list that's set up in a way that this test is expecting. So I want some linked list, it has to be a var. I'm going to call it my list. Linked list node of player locations equals new linked list node of player locations. By the way, this one is optional. And then player location is a class, so I want to create an instance of it. This takes an x and a y as ints, and then a string ID. If you look at the player location class, let's hop over there quickly. Those are doubles. Oh no, yeah, those are supposed to be doubles. Never mind. I thought I messed something up. It's when we get to grid locations, they're ints. I'm still thinking, the compute path method right now. As doubles, so let's put a player at 3.5, 2.7 with an ID of AI3. So I want to make sure my list contains a player with ID AI3 because that's the one that's supposed to be returned. And let's, just for now, put this as null. So I have a linked list of size 1, and then I can assert, not supposed to say assert 0, but I need to compare doubles. So def, let me get my compare doubles real quick. Doubles, D1 double, D2 double, Boolean, math.abs, D1, D2, less than epsilon, val, epsilon double equals 0, 0, 1. And I forgot my equal sign, and then let's format that. So in my compare doubles computed dot x should be 3.5. Y should be 2.7. And player ID should be AI3. So this would be a decent first test case. I have a list of size 1, and I'm making sure that I return the right value. But I want to get a little trickier with my test cases. So I'm going to make sure, and you want to mix up your test cases. If you sit down when you think of your test cases and just build a nice variety of test cases, you shouldn't ever have to worry about my incorrect solutions in Autolab. You should never have to decipher one of my cryptic clues of what the thing is. You should never be doing that. You know, I shouldn't say never, because sometimes I have a fairly tricky one that takes a little bit of time. But you should rarely be doing that. Just sit down and write good test cases, because after 116, that's what you'll have to do. You won't have any hints as to what to test. Just test everything. Look at the homework document. Okay, what do I have to build? Let me test it all. Test it all. Test everything. My list. I'm going to change this. Let's just make it AI1. Yeah, I knew that. I knew it was going to happen. AI2, AI3, AI4. So I want to create a list where my correct solution is somewhere in the middle of this list. And let's change these values to make sure we didn't just get lucky. And then we got a pretty solid test case. We got a list with 4 players in it. We're going to make sure that we grab this player from the middle of the list. Now, writing robust tests, I want a test case where the player I'm looking for is the first element, player I'm looking for is the last element, and a couple where the player I'm looking for is in the middle. One test case where I have a list of size 1 that only contains the player I'm looking for. I want to mix this up quite a bit. Again, I'm backed off a little bit on my incorrect solutions, so probably, I haven't checked, but probably this test case alone might get rid of all my incorrect solutions. This doesn't mean that you're done testing. I mean, if you also pass my test, you know, good for you, you got there, but you should have more tests than just that. But this one might do it for you. I'm going to copy this as a starting point and then do closest player. This one gets a little trickier. It only takes a list of player locations and then returns the player closest to this player. So this player is the player that's calling locate player. So that's player 1. So in my list, I have to make sure somewhere in this list, and mixing this up too is nice. I'm going to put it as the first location. I want to make sure somewhere in my list is player 1, and I want to return the player location for the player closest to player 1, which I purposely set up as AI3, so I don't have to change anything. So closest player, just give it the list. And I expect that to be AI3 because I carefully set this up because I don't want to talk about this method too long because I want to get to the third one and we're running low on time. So player 1 is at 4.5, 7.7. If we look at these two are pretty far off, but this guy, AI3, is pretty close to player 1 and is the closest. In L2 or Euclidean distance, whenever I say L2, I always confuse everybody. But what I mean by that is the way you've computed distance in a 2D space in high school, the square root of the sum of the squares. Okay, and then let's get to this third test case, this third method. So those first two, honestly, those test cases might get rid of all my incorrect solutions for those ones. I'm not going to go that far with task 3 intentionally, even if I had a ton of time. But I do want to talk about what you need to be testing for compute path. For compute path, you're going to take two grid locations, and this is where we are in integers, not in doubles, so we can just use equal for these ones. But a start location, an end location, and return a linked list of grid locations, which will be a path from the start to the end with minimal length and every move being valid. You can only move up, down, left, or right in this grid, and grid will be x, y integers to know what grid location you are, with 0, 0 being the upper left corner. So compute path, again, I need a player because these are all methods of a class, so I need objects of that type so I can call these methods. I can't call methods from a class, I need an object of that type. This is a reference to the calling object. What would this be if I even called it from a class? It wouldn't make sense. So player.compute path, new grid location, 1, 1. I'm just going to pick some locations. New grid location 2, 2. And this is going to be a linked list node of grid location. I have an extra paren here. What did I mess up? Bless you. So I want to compute the path from 1, 1 to 2, 2. Now, of course, in your testing, you'll need more tests. You'll need a bunch, but I just want to set up what a test case would look like for this. So there's 4 things that I want to test with this path. I want to check path.value.x. Let me assert that. I haven't seen that mistake much this semester, I'm happy to say. But I used to see this one quite a bit, where you say, I'm checking it. Why is my test always passing even when it's clearly wrong? You got to make sure your assert's in there. I'm happy that none of y'all have been making that mistake, at least that I've seen this semester. So first, I want to make sure that the first grid location, so path is going to be a reference to the head of the list that's returned, the path that's returned. I want to make sure it starts at the start. So I'm going to make sure it's x, y is 1. Again, these are ints. I can use equal. I also want to check that the last location is going to be 2, 2, the end location. That's a little trickier. I'll leave that one up to you to navigate this list, find the node where next is null, and then making sure that it has x, y of 2, 2. But I'm going to have a problem here. So I have a valid path, which is going to be, I know I need to start at 1, 1 and end at 2, 2. And I can move up, down, left, or right, meaning either my x can change by 1 and my y has to stay the same, or my y can change by 1 and my x has to stay the same. Those are the valid moves, and they can move positive or negative for our up, down, left, right. So I have 2 valid paths. I can either go to 1, 1 to 1, 2 to 2, 2, or I can go to 2, 1 and then 2, 2. These are both valid paths, and these are both correct responses to the method, correct return values. So I have to make sure that I would accept both of these. When it's just 2 correct solutions, this isn't too bad. But if I had like 1, 1 to 5, 5, or like 2, 4 to 10, 12, there's going to be a multitude of correct solutions. So this is a case where we can't just say, did this method return the correct answer? Like for this one, there's only one correct answer for computed, and I'm going to assert that I got the correct answer. But here it gets a little tougher, because we have many correct answers, many potential correct solutions, and if we get any correct solution, our test needs to pass. So if my correct solution in AutoLab returns a different path, maybe I go up and then over, where your code goes over then up, they both need to be accepted by your test case. So this gets a little tricky. I like to do this in 4 steps for this objective. 1, make sure we start at the start. That we already have coded up. That one's easy enough. 2, make sure we end at the end. So every correct solution is going to start at the start and end at the end. 3, make sure we have a path of the length that we're expecting, the minimal length. For example, a correct path could go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 5, 2, 4, 2, 3, 2, 2, it'd be a valid path, but it's not minimal length. So that's incorrect. So make sure the length is minimal. And then finally 4, make sure every move along the path is a valid move. If you check those 4 things and they all check out, then you have a correct solution. And you can say it's good. Kind of a little close today, but that's not bad considering I was answering questions in another lecture and showed up 4 minutes late. So I think we did good there. Have a great weekend. Maybe I'll see you at the hackathon. If I don't, see you all Monday.